Good afternoon and welcome everyone. So today we are going to speak on the topic how we can support multiple display controllers with different or shared interfaces on a single SoC. I'm Devarsh. I work as a software engineering manager at Texas Instruments, and I have with me Aradhya, who is my friend and ex-colleague at TI. So at TI, we have upstream first strategy. We work on various open source projects and try to upstream our software first before rolling out to the SDKs. Okay, so what is the goal of the presentation? If you would have visited our booth, the solutions showcase, you must have seen Beagle Y AI board with running with a big OLD screen connected and running Android, right? In this presentation, what we are going to talk about is the software solution for the display controller that is present in the SoC. So as you can see, it's a quite complicated setup. So you have like two display controllers present in the SoC, and they have like various video ports, and you have multiple interfaces like OLDI, then DPI, which you can feed to HDMI, and the DSI. And these interfaces, if you see closely, they are like some of them are like shared between the display controllers. For example, this OLD can be driven both from the display controller 0 or it can be driven from the display controller 1. Similar case for DPI, which can be driven from either this display controller or the other display controller. And the clocking is equally a bit complicated. We have like 3 PLLs, and like some of the PLLs, they are shared. For example, DSI, the PLL for the DSI can drive OLDI also. Okay, so what do we do about it? It's quite complicated setup, right? Okay, so what we do is like we are going to divide the problem into smaller subblocks. So we'll first see like how a single display controller is modeled in the DRM KMS framework. We'll try to map the smaller subblocks of the display controller to the DRM entities, and we'll see how the display pipeline is set up using a single display controller. Then we'll see how we are going to support these two display controllers in the DRM framework, what are the possible approaches, and then we'll see like how we handle this shared clocking and shared interfaces muxing part, like how we handle this complexity of shared interfaces and the clock PLLs. And lastly, my colleague will ex-colleague would walk you through the bridge drivers that we integrated and what the challenges we faced. All right, so this is a basic display controller block that TI has. So we have like one video pipeline, we have like two video pipelines, and they map to DRM plane structure. So here you will have your video frame buffer data that is stored in the DDR, which can be DMA'd. Then we have this entity called overlay manager, which kind of acts as a video mixer. So it can take as input multiple video pipelines and mix the pixel stream coming from different video pipelines into one pixel stream and pass it on the video port, which also acts as a timing generator, and it can stream the combined pixel data stream to the panel which is connected. So these two hardware entities we map to a single DRM CRTC struct. Then we also create a DRM connector structure and connect to it. All right, so we'll just go through first the basic DRM initialization flow, and that might give us clue on how we can add support for 2 display controllers. So at first, like how many video ports are there? Like for example, in the previous slide, we are like 2 video ports. So based on this, we'll try to create uh, multiple display pipelines iterating through each video port. So we'll try to find out what all bridges are connected to those video ports. This is usually done using the device tree topology. So in the device tree, we would have specified what all bridges or panels are connected to the video ports. We iterate through all of them and save the bridge pointer. Now for each bridge that is found, we try to initialize at least one plane, mark it as a primary plane, and we create one crtc with that primary plane, and we'll try to create an encoder structure also, and we'll try to attach the bridge pointer that was found using the device tree topology to the encoder using this DRM bridge attach no connector flag, and then we try to call the attach API iteratively. So the DRM bridge attach API is kind of a recursive function in the sense that you pass one bridge, then it will try to find next bridge that is connected to it, and it will try to attach to that bridge by calling the bridge attach function for the next bridge. So once we have discovered all the bridges and attached them, we'll try to connect those bridges to the connector and create a populate DRM connector, and lastly we'll register the DRM device which will create a /dev DI card which your display server can use. Alright, so now how do we support 2 display controllers, right? So one possible solution is like you can model both the hardware DSS display hardware blocks as a single display controller block in the software. Like you create an abstract display controller subsystem which is kind of managing both the hardwares internally. So for this what we can do is like we'll populate each overlay manager plus video port combination as a CRTC, as a unique CRTC, irrespective of whether it's in hardware block 1 or hardware block 2. So for example, here we have like 4 video ports and the overlay managers, right? So we'll create 4 CRTCs for this list of video ports and link it to a single DRM card. And similarly, we'll enumerate all the 4 pipelines as well as if it is managed by a single display controller. And so from the user perspective, if they try to dump the mode test output, right, they would see that there are like 4 CRTs, 4 video planes, and the 4 connectors that are connected to the display subsystem. And once the user tries to drive whichever CRTC based on the CRTC ID and the plane ID, those things will go to the DRM framework, and driver would then internally see that okay, this CRTC is managed by the hardware block 1. Then it will try to set up the corresponding registers and the power domains that are required for that hardware block and try to initialize the pipeline. So there are advantages because it gives an abstracted view to the end user and the display server. Like it's just a single display controller with so many video planes and so many CRTCs, and it's quite simple to control that using a single process. But there are challenges. The complexity gets transferred to your display controller driver, and so it has to always translate like okay, this CRTC, what is the register space, what is the power domain. So it has to manage and power on the corresponding power domains separately because each block has separate power domains. And one more challenge is like since we have only single DRI card or a single DRM device, so there's a single GenPD assigned, and with the single GenPD assigned, you cannot control both the power domains separately. So it's like we'll have to control both the power domains together and unnecessarily power on second block as well, even if it's unused. And let's say if your use case is like you want to run two separate DRM applications in parallel, and so that won't be possible because you only have a single card, so only a single application or a single DRM master can control the whole hardware block. The other use case that is not possible with this is like, let's say you want to control this one display controller by Linux and the other by the RTOS, then that kind of partitioning is also not possible with this. So we took another approach, it's called a dual card approach. So we enumerate both the display controllers as a separate DRM card, and with this there is good amount of software reusability, like we try to reuse the existing software support for the previous SoCs and try to reuse those compatibles. And we have the display sharing atomicity as well. If one block we are not using, then we can relinquish it to another microcontroller in the heterogeneous subsystem. There's good power management story because each hardware block is a separate DRM device, so we have unique Gen PD, and we can atomically control each hardware block based on the usage, based on what the end application or which blocks the hardware end application is using. And in the display servers as well, there is support for having this multiple DRM cards. For example, in Western you can pass this additional device property, and it will then render using both the cards. Like you will get an extended view of your display context that we are getting from the GPU, that is spread across both all the connectors that are connected in the both the DSS, and similar support is there in the Android display server as well. Okay, so what do we do about clocks and muxes now that we have solved the dual card story? So we try to transfer that complexity to the device manager firmware. So like if I have to set the mux for this OLDI-TX1, I want to drive from the second display controller and not the first one, then I need to set this mux for the data path and this mux for the clock path. So what we can do is like we can just set the assign clock property in the device tree, set the ID for the corresponding mux that is need to be configured, and the device manager firmware will take care of setting the respective muxes to route the OLDI-TX1 to the second DSS. And same case for the pixel clock as well. So in the pixel clock, if you want to set the mux and choose the right clock based on your use case and the interface, you can just set the assigned clock and to the respective mux, and that will be taken care of by the device manager firmware. Okay, so now we have solved the mux story as well, but now as we are creating two cards, we don't want to create a new separate structure for supporting this story. We want to reuse the existing display controller compatibles and the structures that are already present in the driver. So we did some framework cleanups in the driver. So whatever the SoC specific fields were there and the different compatibles that support the display controllers, for example the clocking related fields, we tried to separate them out. We removed all these clocking fields and we try to make a generic structure that is can be reused across the various SoCs, and we try to get this pixel clock fields from the device manager directly, like if you are connecting the monitor, and based on the aided whichever resolutions the monitor supports, we try to enumerate those and check if the device manager is able to set the clocks and it's able to support that much pixel clock frequency. We try to cache those values in the successful rate field for those values which are able to pass, and the attempted rate field which we attempted. So this way we don't have to query the each pixel clock value for the max again and again. We can first check in this array, and based on that we can deduce that okay, this clock can be supported in this SoC. So this is how the device tree looks like. We have like two display controller nodes, we try to reuse the existing compatible for the previous gen SoC because we are using that structure, but we still have a new compatible created in case in future we want to add some tweaks or some code that is specific to the SoC for 62P. And that's how like power domains are separate, clocks are separate. We set the assigned clocks based on the muxes we want to set, and this kind of creates the two DRM cards by using the same 6.2 structure that we had previously. Okay, so now my friend will walk you through the different interfaces we support and how they are shared across the display controllers and what complexities we solve. Thank you.
Thanks, Devarsh. All right. So here is a slightly simplified diagram of the DSS that we want to support. Not only do we have shared interfaces like the OLDI up above, but we also have video ports that are supporting multiple interfaces in the second DSS. You can see the video ports over there are supporting, for example, the first one is supporting the DPI output or the OLDI1 output, and the second video port is supporting DPI again, as well as DSI. So to be able to discover which one we want to support at any point of time, we had to get a few changes done inside the framework, and that's what I'll walk you through. First, I want to talk about the OLDI, the LVDS. So just to give you all a lay of the land, LVDS, this here is a picture of a single link connection of the LVDS. LVDS is a signaling-based protocol where differential pair-based protocol where the videos, 3 or 4 pairs of video signals, the differential pair cancels out the noise and you can use them in remote display setups. So this was an earlier gen setup that we had. The single CRTC or the single video port was supporting the one OLD transmitter in a one-to-one fashion. So, and this was a mid-gen setup where, again, the same video port, same CRTC would then support 2 OLD transmitters. The benefit of having this situation is that you can essentially double the bandwidth of video data without having to double the frequency that the OLD transmitters are supporting. So coming back to the 6.2p. Now, we have two DSSs again, and 2 video ports that are supporting the OLD1 video output. And that was a shared resource for us. So what we had to, in the previous generations, the situation was that since there was a one-to-one situation between the DRM CRTC and the OLD transmitter, what we do is we just have it coupled with the DRM CRTC, and it was not separate. The same hardware would get enabled while the video port was getting enabled through the DRM CRTC. So the solution was that we had to separate out all the OLD transmitter bits, and we decided that we'd register the OLD transmitter as a different bridge itself, as a DRM bridge, and that would allow the OLD to be acting completely independently, and we would have the flexibility to control which video source did we want to use. So for an integration that does not use the second DSS, this is the dual link. We'd have this sort of connection. And so, okay, the device tree is a bit wonky, but yeah, so I just wanted to mention that we have the DSS, which is supporting same DSS, supporting 2 OLD transmitters, which interconnect each other with the highlighted properties, which is the companion OLD and the secondary OLD. So with the companion, we are passing the node reference of the secondary OLD. And then the 2 OLDI transmitters are supporting one single bridge. So as you can see, one single display panel. And as you can see, the single display panel has 2 input ports coming from 2 different OLD transmitters. And the OLD transmitters are being input from one single port within the display driver with 2 endpoints. And this is the other configuration that we were supporting. We had DSS 0 and DSS 1, both driving single link OLDI outputs completely independently. So the difference between the previous device tree and this device tree was that we now have, over to the left, we have two display panels. They both don't have two input ports anymore. It's just one input port. And we have two OLD transmitters. They're not interconnected at all. And they are being sourced by two DSSs on the right with, with one output ports each. So the OLD bridge up until this point was integrated recently into the main line, but there is still some work that needs to be done. There is something called the clone mode, where a single video port would support two different encoder-bridge pipelines within the DRM framework. And what we want is that in the clone mode, both the pipelines be simultaneously active. So here is what the DRM-based pipeline would look like. We have a plane. We have one CRTC that's providing the video buffer to the, we have the plane which is providing video buffer data to the CRTC. We have two encoders at this point. We are branching out. We have two encoders, E00 and E01, and they individually are trying to support two independent bridge pipelines. The ask is that the same video from plane 0 be transmitted to both the pipelines. So when we tried to do this, we had to use the possible clones field within for the encoders. So that allows us allows E00 and E01 to be able to integrate to the same CRTC. But that did not happen. What happened was the other plane within the whole the other plane that we had registered, what would happen is it would get utilized for the second pipeline, and both the planes would be filled up with the same video buffer data, but well, we didn't want that. We wanted plane 0 and CRTC 0 to be rendering the same video buffer and providing to two different pipelines because, well, they were in the clone mode. The problem with that was there was another CRTC encoder pipeline which would support connector 10, and this pipeline would then be left with no plane. So the plane 1 was actually intended for CRTC 1, but whenever we try to run all the displays, the first one in the clone mode, the second one a separate link, that would not happen. So it's still a work in progress. I just walk you through the clone mode device tree, what it would look like once the work is finished. We have two display panels over there, which are supported by two independent but synchronized OLD transmitters, which are then being sourced by the same DSS output. All right. So I'll come to the DSI set of problems now. This is the other use case that we support in the AM62P. It's a DSI-based pipeline. The SoC outputs DSI signals, and we have a panel which is connected outside. So this is the encoder-bridge and CRTC pipeline that would look like. We have CRTC, we have encoder, which is virtual within the DSS. The bridge 0 is the DSI transmitter, also within the SoC. We have bridge 1, which is the DSI RX that's available on the panels, and the panel bridge, which is bridge 2, which is a virtual entity created by the DRM framework. So I'll just walk you through the enabling sequence of. So when we are trying to display a new frame on the output, this is what the enable sequence looks like. So the CRTCs get enabled first using the atomic enable API. Then the bridges get pre-enabled from last to first. So bridge 2 pre-enables, bridge 1 pre-enables, bridge 0 pre-enables. Then comes in the encoder, and then the bridges get finally enabled from first to last. So here the DSS, the CRTC, is starting its pixel stream from CRTC enable, while the DSI TX would exit the LP11 and would be able to would be ready to accept video signals at bridge 0 atomic enable. So this was a major problem for us, because having the video signals be transmitted way early than DSI was ready to accept the actual video data was causing all sorts of issues. So the FIFO buffers inside the DSI IP that we had was being corrupted. The timings were getting mismatched, and eventually the output on the display DSI panel would, the colors would get all wonky and shifted. So the fix essentially, well, it sounded simple, but we had to, the fix was to switch the whole sequence so that the DSS would start its pixel stream way a little after the DSI was made ready to accept the video signals. So this is, so we had a couple of patch series that was sent out to support this, and this again was accepted into the 6.17 RC1 recently, and this is what the new sequence looks like. Now the bridges get pre-enabled initially before CRTC enable happens, and the pre-enable again happens from last to first. So in bridge 0 atomic pre-enable, the DSI is able to exit LP11 and is now made ready to be able to accept the video signals. So once that is done, the CRTC enable is being called, where the DSS starts its pixel stream. The encoder enable follows, and then the bridges finally get enabled. So what we had to do was we had to move the enabling of DSI bridge from the enable API to the pre-enable API to be able to support the whole thing. All right, so a few references. We have the reference manuals, we have an app note, a staging GitHub URL where we have all the patches to get your to get the panels and displays up and ready over Linux Next. So, but yeah, we had to, a few of the series that were recently merged, and yeah, in the couple months. So a few of the next level items that we are on. So the Western supports only extended mode when two different DRM cards are being involved. And we need to be able to try a clone. Two different DRM cards would be supporting same video buffer output. We are on the way to integrate and validate more DSI panels. A little optimization for DSI bridges and panels so that they are up early for automotive use cases. And so the oldie clone mode using a single plane that I talked about earlier. And here is a display of the, a demo of the triple display setup that we had. On the right, we have a DSI RPI panel. In the center, we have the LVDS panel. And in the left, we have an HDMI monitor over DPI. Credits and acknowledgement, and that's it. Thank you so much. Thank you so much. Any questions? Yeah.
In the new proposal where you were solving this issue of video getting enabled before the DSI has been started, and now your proposal is to start, come out of LP11 in the pre-enable phase itself.
That's right.
But what about when there is a need to send commands over video buffer or something within the pre-enable phase for the panels?
Okay, the DSI transmitter over there was a fair exception in the sense you needed it to be running way before. But if you have, if you do have, so within the same pre-enable API, if you want to send some initial signals that you do using the usual pre-enable phase, you just push them up earlier in the same pre-enable API. We did have an initial proposal for the changing of sequence where we had an early enable and late disable APIs that we wanted to have. So that would keep the pre-enable and post-disable APIs just right where they were. And there were 2 new sets of APIs doing bridge operations. But then the maintainers suggested that we remove pre-enable from its then current place, move it up before CRTC. So yeah.
Yeah, and like there are also like various hooks in the framework. As in, let's say you have a DSI panel, and there is a requirement that the bridge that is before the that DSI panel needs to be enabled first or initialized first. Then in your panel driver, you can set prev-enabled first as true, and it will try to initialize the bridge before that first and then initialize your panel. And let's say if you don't want it, like you want to initialize your panel in the low power mode itself, then you can set that flag as false and initialize the panel. And then using these hooks that you shared, right, you can start to the video mode and then carry the rest of the initialization. Yeah.
I did not understood why the clock has to be initialized in the DM and not in Linux anymore.
Yeah, so that's like this particular SoC we are talking about is like a 62P SoC where we have the device management solely controlled by the R core, and it's a separate controller that is on charge of power management and the device core management. But in other SoCs where we have like 62L, we have the CMI support being run on the same core. But it's like it's a secure operation, so we want to control that via a separate entity and a separate host. And these clocks are shared across different cores as well. So it's a heterogeneous system. Like we have RTOS also running and sometimes taking control of the display subsystem. So in that case, the clocks and the resources need to be controlled by a central entity because it's being shared across different hosts. Thank
you. Does anyone else have any more questions? All right. Thank you so much. Really appreciate you guys coming out and seeing the talk. Thank you.